So I got to start by telling you the syllabus for this term, not the detailed one, just big game plan. The game plan is we will do electromagnetic theory. Electromagnetism is a new force that I will introduce to you and go through all the details. And I will do optics. And optics is part of electromagnetism. And then near the end, we will do quantum mechanics. Now, quantum mechanics is not like a new force. It's a whole different ballgame. It's not about what forces are acting on this or that object that make it move or change its path. The question there is, should we be even thinking about trajectories? Should we be even thinking about particles going on any trajectory? Forget about what the right trajectory is. And you will find out that most of the cherished ideas get destroyed. But the good news is that you need quantum mechanics only to study very tiny things, like atoms or molecules. Of course, the big question is, where do you draw the line? How small is small? Some people even ask me, do you need quantum mechanics to describe the human brain? And the answer is yes, if it is small enough. So I've gone to parties where after a few minutes of talking to a person, I'm thinking, okay, this person's brain needs a fully quantum mechanical treatment. But most of the time, everything macroscopic, you can describe the way you do with Newtonian mechanics or electrodynamics. You don't need quantum theory. All right, so now we'll start with the brand new force of electromagnetism. But before doing the force, I got to remind you people of certain things I expect you all to understand about the dynamics between force and mass and acceleration that you must have learned last term. I don't want to take any chances. I'm going to start by reminding you how we use this famous equation of Newton So we have seen this equation probably in high school, but it's a lot more subtle than you think. Certainly a lot more subtle than I thought when I first learned it. So I will tell you what I've figured out over these years on different ways to look at F equals ma. In other words, if you had the equation, what's it good for? The only thing anybody knows right away is A stands for acceleration, and we all know how to measure it. By the way, anytime I write any symbol on the board, you should be able to tell me how you'll measure it. Otherwise, you don't know what you're talking about as a physicist. Now, acceleration, I think I won't spend too much time on how you measure it. You should know what instruments you will need. So I will remind you that if you have a meter stick or many meter sticks and clocks, you can follow the body as it moves. You can find its position now, its position later, take the difference, divide by the time, you get velocity. Then find the velocity now, find the velocity later, take the difference, divide by time, you get acceleration. So acceleration really requires 3 measurements, 2 for each velocity. But we talk of acceleration right now because you can make those 3 measurements arbitrarily near each other, and in the limit in which the time difference between them goes to 0, you can talk about the velocity right now and acceleration right now. When you're in your car, the needle points at 60, that's your velocity right now. It's an instantaneous quantity. And if you step on the gas, you feel this push, that's your acceleration right now. That's the property of that instant. So we know acceleration, but the question is, can I use the equation to find the mass of anything? Now, very often when I pose the question, the answer given is, go to a scale, weighing machine, and find the mass. And as you know, that's not the correct answer because the weight of an object is related to being near the Earth due to gravity, but the mass of an object is defined anywhere. So here's one way you can do it. Now you might say, well, take a known force and find the acceleration it produces, but we haven't talked about how to measure the force either. All you have is this equation. The correct thing to do is to buy yourself a spring, then go to the Bureau of Standards and tell them to loan you a block of some material, forgot what it is. That's called a kilogram. That is a kilogram by definition. There is no God-given way to define mass. You pick a random entity and say that's a kilogram. So that's not right and that's not wrong. That's what a kilogram is. So you bring the kilogram, you hook it up to the spring, and you pull it by some amount, maybe to that position, and you release it. You notice the acceleration of the 1 kilogram, and the mass of that thing is just 1. Then you detach that mass. Then you ask, then the person says, what's the mass of something else? I don't know what the something else is. Let's say potato. Then you take the potato or anything, elephant, here's potato. You pull that guy by the same distance. And you release that, and you find its acceleration. Since you pulled it by the same amount, the force is the same. Whatever it is, we don't know what it is, but it's the same. Therefore, we know the acceleration of 1 kilogram times 1 kilogram is equal to the unknown mass times the acceleration of the unknown mass. That's how, by measuring this, you can find what that mass is. So in principle, you can find the mass of everything. So imagine masses of all objects have been determined by this process. Then you can also use F equal to ma to find out what forces are acting on bodies in different situations. Because if you don't know what force is acting on a body, you cannot predict anything. So you can go back to the spring and say, I want to know what force the spring exerts when it's pulled by various amounts. Well, you pull it by some amount x, you attach it to a known mass, and you find the acceleration. And that's the force. And if you plot it, you will find F as a function of x will be roughly a straight line, and it will take the form F equals minus kx. That k is called the force constant. So this is an example of you're finding out the left-hand side of Newton's law. You've got to understand the distinction between F equals minus kx and F equals ma. What's the difference? This says if you know the force, I can tell you the acceleration. But it's your job to go find out every time what forces might be acting on a body. If it's connected to a spring, and you pull the spring and it exerts a force, someone's got to make this measurement to find out what the force will be. All right, so that's one kind of force. Another force that you can find is if you're near the surface of the earth, if you drop something, it seems to accelerate towards the ground. And everything accelerates by the same amount, g. Well, according to Newton's laws, if anything is going to accelerate, it's because there's a force on it. Therefore, the force on any mass m must be mg, because if I divide by m, I got to get g. So the force on masses near the earth is mg. That's another force. Something interesting about that force is that unlike the spring force, where the spring is touching the mass, you can see it's pulling it, or when I push this chair, you can see I'm doing it. The pull of gravity is a bit strange because there is no real contact between the earth and the object that's falling. It was a great abstraction to believe that things can reach out and pull things which are not touching them. And gravity was the first formally described force for which that was true. And another excursion in the same theme is if this object gets very far, say like the moon over there, then the force is not given by mg, but the force is given by this law of gravitation for r very near the surface of the earth. If you put r equal to the surface of the earth, you will get a constant force that is just mg. But if you move far from the center of the earth, you got to take that into account, and that's what Newton did, and realized the force goes like 1 over r squared. So every time things accelerate, you got to find the reason, and that reason is the force. Many times, many forces can be acting on a body, and if you put all the forces that are acting on a body, and that explains the acceleration, you're done, but sometimes it won't. That's when you have a new force. And the final application of F equals ma is this one. If you knew the force, for example, on a planet, I mean, here's a planet going around the sun, and it's here. This is the sun, and you know the force acting on it, given by Newton's law of gravity. You can find the acceleration that'll help you find out where it'll be 1 second later, and you repeat the calculation, you will get the trajectory. So F equals ma is good for three things. That's what I want you to understand. To define mass, to calculate forces acting on bodies by seeing how they accelerate, and finally, to find the acceleration of bodies given the forces. This is the cycle of Newtonian dynamics. And what I'm going to do now is to add one more new force, because I'm going to find out that there is another force not listed here. I'm going to demonstrate to you that new force. Okay? Here's my demonstration, the only demonstration you will see in my class, because everything else I've tried generally failed. But this one always works. So I have here a piece of paper. Okay? Then I take this trusty comb, and I comb the part of my head that's suited for this experiment. Then I bring it next to this, and you see, I'm able to lift that. Now, that's not the force of gravity, because gravity doesn't care if you comb your hair or not. Okay? And also, when I shake it, it falls down. So you're thinking, okay, maybe there is a new force, but it doesn't look awfully strong because it's not able to even overcome gravity, because it eventually yielded to gravity and fell down. But there's actually a mistake to think so. In fact, this new force that I'm talking about is 10 to the power 40 stronger than gravitational force. I will tell you by what metric I came up with that number. But it's an enormously strong force. You got to understand why I say it is such a strong force when I shook it, the thing fell down. So the reason is that if you look at this experiment, here's the comb and here's the paper. The comb is trying to pull the paper. But what is trying to pull it down? What is trying to pull it down? So here is me. Here's that comb. Here's the paper. The entire planet is pulling it down. Himalayas, pulling it down. Okay? Pacific Ocean, pulling it down. Bin Laden sitting in his cave, pulling it down. Everything is pulling it down. Okay? I'm one of these people generally convinced the world is acting against me, but this time I'm right. Okay? Everything is acting against me, and I'm able to triumph against all of that with this tiny comb. And that is how you compare the electric force to the gravitational force. It takes the entire planet to compensate whatever tiny force they create between the comb and the piece of paper. To really get a number out of this, I'll have to do a little more, but I just want to point out to you, this is a new force, much stronger than gravitation. So I want to tell you a few other experiments people did without going into what the explanation is right now. But let me just tell you, if you go through history, what all did people do? So one experiment you can do, you take a piece of glass and you rub it on some animal that's passing by. Okay? Water buffalo. That's why I cannot do all the experiments in class. You rub it on that guy, then you do it to a second piece of glass, and you find out that they repel each other, meaning if you put them next to each other, they tend to fly apart. Then you take a piece of hard rubber, and you rub that on something else. I forgot what, silk, Yeti, some other thing. Then you put that here, so I'll give a different shape to that thing. That's the rubber stick. And you find, when you do that to this, these two attract each other. So sometimes they repel, sometimes they attract. Here's another thing you can do. By some nylon thread, you hang a small metallic sphere, and you bring one of these rods next to it, doesn't matter which one. Initially, they're attracted, and suddenly, when you touch it and you remove it, they start repelling each other. What's going on? That's another thing you could do. Last thing I want to mention is, if you took two of these things which are repelling each other, let's say. Let's say they're attracting each other like this. Then you connect them with a piece of nylon and you take it away, nothing happens. If you connect them with a piece of wire and take away the wire, they no longer attract each other. So these are examples of different things. I'm just going to say, you do this, you do this, you do that. Then finally, you need a theory that explains everything. So that's the theory that I'm going to give you now. That's the theory of electrostatics. And I don't have time to go into the entire history of how people arrived at this final formalism. So I'm just going to tell you one formula that really will explain everything that I've described so far. And that formula is called Coulombs law. Even though Mr. Coulomb's name is on it, he was not the first one to formulate parts of the law, but he gave the final and direct verification of Coulomb's law. There are other people who had contributed to it. So Coulomb's law says that certain entities have a property called charge. You have charge and you don't have charge. But if you have charge, the charge that you have, you meaning any of these objects, is measured in coulombs. Anyway, that was not Coulomb's idea to call it Coulomb. Whenever you make a discovery, you're breathlessly waiting that somebody will name it after you. But it's not in good taste to name it after yourself. But it carries Coulomb's name. So he didn't say, call it Coulomb. Okay? But he certainly wrote down this law. The law says that if you've got one entity which has some amount of charge called Q1 and has another entity that's some amount of charge Q2, they will exert a force on each other, which is given by Q1, Q2 times this constant, which is somehow written as 1 over 4 pi epsilon 0 times 1 over r squared. But r is the distance between them. Now you can ask in this picture, what do you mean by distance? I mean, is it from here to there, or is it from center to center? We are assuming here that the distance between them is much bigger than their individual sizes. For example, you say, how far am I from Los Angeles? Well, 3,225 miles. But you can say, are you talking about your right hand or your left hand? Well, I'm a point particle for this purpose, so it doesn't matter. So here we are assuming that either they're mathematically point charges, or they're real charges with a finite size, but separated by a distance much bigger than the size. So r could stand, if you like, for center to center. Doesn't matter too much. So this is what Coulomb said. Now, if you look at this number here, 1 over 4 pi epsilon 0, its value is 9 times 10 to the 9. What that means is the following. If you take 1 coulomb of body with 1 coulomb of charge, another body with 1 coulomb of charge, and they're separated by 1 meter, then the force between them will be this number. Because everything else is a 1, it'll be 9 times 10 to the 9 newtons. That's an enormous force. And normally you don't run into 1 coulomb of charge. But the reason why a coulomb was picked is sort of historical, and it has to do with currents and so on. But anyway, this is the definition. Now, if you want to be more precise, I should write a formula more carefully, because force is a vector. Also, I should say force on whom and due to what. So let's say there are 2 charges, and say Q1 is sitting at the origin and Q2 is sitting at a point whose position is the vector r. Then the force on 2 due to 1 is given by Q2, Q1 over 4 pi epsilon 0 times 1 over r squared. That's the magnitude of the force. But I want to suggest that the force is such that Q1 pushes Q2 away. So I want to make this into a vector, but I got the magnitude of the vector. As you know, to make a real vector, you take its magnitude and multiply it by a vector of unit length in that same direction. The unit vector we can write in many ways. One is to say E sub r. E sub r is a standard name for a vector of length 1 in the direction of r. But I'll give you another choice. You can also write it as r divided by the length of r. That also will be a vector of unit length parallel to r. So there are many ways to write the thing that makes it a vector. And F21 is minus of F12. Now, how do we get attraction and how do we get repulsion? We get it because Q1 and Q2, if they're both positive, and if you use the formula, you will find they repel each other. But if they're of opposite signs, you will do the same calculation, but you'll put a minus sign in front of the whole thing. That'll turn repulsion into an attraction. So you must allow for the possibility that Q can be of either sign. Q can also be 0. There are certain entities which don't have any electric charge, so if you put them next to 1,000,000 coulombs, nothing happens. So some things have plus charge, some things have minus charge, some things have no charge. But they're all contained in this Coulomb's law. Now, again, skipping all the intermediate discoveries, I want to tell you a couple of things we know about charge. First thing is, Q is conserved. Conserved is a physics term for saying does not change with time. For example, when you say energy is conserved, it means particles can come and collide and do all kinds of things, but if you add that energy before, you will get the same answer afterwards. Whenever that happens, the quantity is conserved. The claim is electrical charge is conserved. So electrical charge may migrate from A to B or B to A, but if you add up the total charge, say in a chemical reaction or in any process, including in big particle accelerators, where things collide and all kinds of stuff come flying out, the charge of the final products is always equal to the charge of the incoming products. But charge conservation needs to be amended with one extra term, extra qualification. It's called local. Suppose I say the number of students in the class is conserved. That means you count them any time, you got to get the same number. Well, here's one possibility. Suddenly, one of you guys disappears and appears here at the same instant. That's also consistent with conservation of student number because the number didn't change. What disappeared there appeared here. But that is not a local conservation of charge because it disappears in one part of the world and appears in another one. And it's not even a meaningful law to have in the presence of relativity. Can any of you guys think of why that might be true? Why charge disappearing somewhere and appearing somewhere else cannot be a very profound principle? Yes? Yep.
Well, if it's in the same instant disappearing from one place and appearing in another place, it's traveling faster than light.
Well, we don't know that it was the same thing that even traveled. It may not have traveled. It may even be. No, here's another thing. Suppose an electron, suppose a proton disappears there and a positron appears here. That still conserves charge, but we don't think that the proton traveled and became the positron, right? So it is not that it has traveled. You're right. I think I hadn't thought about that. It's a good point that it implies it traveled infinitely fast. But that's not the reason you object to it. Yep?
It's not necessarily simultaneous.
That is the correct answer. His answer is it is not simultaneous in every frame of reference. You must know from special theory that if two events are simultaneous in one frame of reference, if you see those same two events in a moving train or plane or anything, they will not be simultaneous. Therefore, in any other frame of reference, either the charge would have been created first and then after a period of time reappeared somewhere, destroyed somewhere and appeared after a delay. Or the appearance could take place before the destruction. So suddenly you got two charges. So conservation of charge, which is conserved non-locally, cannot have a significance except in one frame of reference. But if you believe that all observers are equivalent and you want to write down laws that make sense for everybody, it can only be local. So electrical charge is conserved and it is local, locally conserved. In other words, stuff doesn't just disappear, stuff just moves around. You can keep track of it, and if you add it up, you get the same number. The second part of Q, which is not necessary for any of these older phenomena, is that Q is quantized. That means the electrical charge that we run into does not take a continuum of possible values. For example, the length of any object, you might think, at least in classical mechanics, is any number you like. It's a continuous variable. But electric charge is not continuous. As far as we can tell, all the charges we have ever seen are all multiples of a certain basic unit of charge, which turns out to be 1.6 times 10 to the minus 19 coulombs. Every charge is either that or some multiple of it. Multiple could be plus or minus multiple. So charge is granular, not continuous. Okay, so I'm going to give you a little more knowledge we have had since the time of Coulomb that sort of explains these things. Namely, what's really going on microscopically. We don't have to pretend we don't know. We do, so we might as well use that information from now on. What we do know is that everything is made up of atoms, and that if you look into the atom, it's got a nucleus, a lot of guys sitting here. Some are called protons and some are called neutrons, and then there are some guys running around called electrons. Of course, we will see at the end of the semester that this picture is wrong, but it is good enough for this purpose. It's certainly true that there are charges in an atom which are near the center and other light charges which are near the periphery or outside. All things carrying electric charge in our world, in daily life, are either protons or electrons. You can produce strange particles in an accelerator. They would also carry some charge, which will in fact be a multiple of this charge, but they don't live very long. So the stable things that you and I are made of, and that just about anything in this room is made up of protons, neutrons, and electrons. The charge of the neutron, as you can guess, is 0. The charge of the electron, by some strange convention, was given this minus sign by Franklin. And the charge of the proton is plus 1.6 times 10 to the minus 19 coulombs. There are a lot of amazing things I find here. I don't know if you've thought about it. First interesting thing is that every electron anywhere in the universe has exactly the same charge. It also has exactly the same mass. Now you might say, look, that's a tautology, because if it wasn't the same charge and if it wasn't the same mass, you will call it something else. But what makes it a non-empty statement is that there are many, 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 many electrons which are absolutely identical. Look, you try to manufacture 2 cars. The chance that they're identical is 0, right? I got one of those cars, so I know that. Doesn't work. It's supposed to. So despite all the best efforts people make, things are not identical. But at the microscopic level of electrons and protons, every proton anywhere in the universe is identical. And they can be manufactured in a collision in another part of the universe. This can be manufactured at a collision in Geneva. The stuff that comes out, identical. That is a mystery. At least in classical mechanics, it's a mystery. Quantum field theory gives you an answer to at least why all electrons are identical, and why all protons are identical. The fact that there are absolutely identical particles is very, very important. It also makes your life easy, because if every particle was different from every other particle, you cannot make any predictions. We know that the hydrogen atom on a receding galaxy is identical to the hydrogen atom on the Earth. That's why when the radiation coming from the atom has a shifted wavelength or frequency, we attribute it to the motion of the galaxy. And from that we deduce, from the Doppler shift, we find out its speed. But another explanation could be, well, that's a different hydrogen atom. Maybe that's why the answer is different. But we all believe it's the same hydrogen atom, but it's moving away from us. Therefore, one of the remarkable things is that all electrons and all protons are equal. But a really big mystery is, why is the charge of the electron exactly equal and opposite to the charge of the proton? They are not the same particle. Their masses are different. Their other interactions are different. But in terms of electrical charge, these two numbers are absolutely equal as far as anybody knows. That's another mystery. Two different particles, not related by any manifest family relationship, have the same charge, except in sign. And there are theories called grand unified theories which try to explain this, but it's certainly not part of any standard established theory. But it's key to everything we see in daily life, because that's what makes the atom electrically neutral. Okay, now we can understand the quantization of charge, because charge is carried by these guys, and these guys are either there or not there, so you can only have so many electrons. You cannot have a part of an electron or part of a proton. Now, let's try to understand all these experiments in terms of what we know. First of all, when you take this piece of glass and you rub it, the atoms in glass are neutral. They got equal number of protons and electrons. But when you rub it, the glass atom loses some electrons to whatever you rubbed it on. Therefore, it becomes positively charged because some negative has been taken out. In the case of the rubber stick, it gains the electrons, and whatever animal you rubbed it on, it loses the electrons. So actually, real charge transfer takes place only through electrons. Protons carry charge, but you're never going to rip a proton out unless you use an accelerator. It's really deeply bound to the nucleus. But electrons are the one who do all the business of electricity in daily life. The current flowing in the wire, in your circuit, it's all motion of electrons. So from this and Coulomb's law, can you understand the attraction between these two? How many people think you can, from Coulomb's law, understand the attraction between these two rods? Nobody thinks you can. Well, why do you think you cannot? You know why?
Because they're on point charges.
Okay. Any other reason why Coulomb's law is not enough? Well, how will you apply Coulomb's law to understand the attraction between these two rods? What will you have to do?
You'd have to apply to F equals ma?
No, that will, once you got the F, the A will follow. But can you compute the force between two rods, one of which has got a lot of positive charge, one of which has a lot of negative charge, given Coulomb's law? Yes.
You don't know the exact quantities of the charges?
Pardon me?
You don't know the exact
Suppose I tell you,
charges?
I tell you how many charges there are. Yes.
You don't know which direction the attraction.
No, we do know, because the plus and minus will be drawn towards each other. Okay, I'll tell you what it is. It's an assumption we all make, but you're not really supposed to make it. It's not a consequence of any logic. Coulomb's law talks about two charges, 2 point charges. What if there are 3 charges in the universe? What is the force this one will experience due to these two? This is Q1, this is Q2, this is Q3. Coulomb's law doesn't tell you that. It tells you only 2 at a time. But we make an extra assumption called superposition, which says that if you want the force on 3, when there is Q1 and Q2, you find the force due to Q2, and you find the force due to Q3, and you add them up. The fact that you can add these two vectors is not a logical requirement. There's no, in fact, it's not even true at an extremely accurate level that the force between 2 charges is not affected by the presence of a third one. But it's an excellent approximation, but you must realize it is something you've got to find to be true experimentally. It's not something you can say is logical consequence. Logically, there's no reason why the interaction between 2 entities should not be affected by the presence of a third one. But it seems to be a very good approximation for what we do. And that's the reason why eventually we can find the force between an extended object and another extended object by looking at the force on every one of these due to every one of those and adding all the vectors. Okay, so superposition plus Coulomb's law is what you need. Then you can certainly understand the attraction. How about the comb and the piece of paper? That's a very interesting example, and it's connected to this one. See, the piece of paper is electrically neutral. So let me do paper and comb instead of this one. It's got the same model. Here's the piece of paper. Here's the comb. The comb is positively charged. The paper is neutral. So in a way, there's nothing here to be attracted to this one. But if I bring it close enough, there are equal amount of positive and negative charges. But what will happen is the negative charges will migrate near these positive charges from the other end, leaving positive charges in the back. So that the system will separate into a little bit of negative closer to the positive, and the leftover positive will be further away. Therefore, even though it's neutral, the attraction of plus for this minus is stronger than the repulsion of this plus with this plus. That's called polarization. So polarization is when charge separates. Some materials cannot be polarized, in which case, no matter how much you do this with a comb, it won't work. Some materials can be polarized. The piece of paper is an example of what can be polarized. We can understand that too. And in this example, if you bring a lot of plus charges here, and you look at what's going on here, the minus guys here will sit here, the plus will be left over in the back, and then this attraction between plus and minus is bigger than this repulsion, so it will be attracted to it. But once it touches it, this rod touches that, then what you have is a lot of plus charges here. They repel each other. They want to get out. Previously, they couldn't get out. They're stuck on the rod. But now if you make contact, some of them will jump to that one. Then when you separate them, you will have a ball with some plus charges, and you will have a rod with more plus charges, and they will repel each other. And finally, I said if you take two of these spheres, suppose one was positively charged, one was negatively charged, they are attracting each other. If you connect them with a nylon wire or a wooden stick, nothing happens. But if you connect them with an electrical wire, what happens is that the extra negative charges here will go to that side. Then when you are done, they will both become electrically neutral. Okay, so that's why. So the point of this one is electric charges can flow through some materials but not other materials. If it can flow through some materials, it's called a conductor. If it cannot flow through them, it's called an insulator. So in real life, you got both. So when you're changing the light bulb, if you don't want to get an electric shock, you're supposed to stand on a piece of wood before you stick your finger in, unless you got other intentions. Then you will find that you don't get the shock because the wood doesn't conduct electricity. But if you stand on a metallic stool on a metallic floor and put your hand in the socket, you'll be part of an electrical circuit. Human body is a good conductor of electricity, but what saves you is that it cannot go from your feet to the floor. Now, there are also semiconductors, which are somewhere in between. But in our course, either we'll talk about insulators, which don't conduct electricity, or imperfect conductors, which conduct electricity. Okay, so summary of what I've said so far is that there's a new force in nature. To be part of that game, you have to have charge. If you have no charge, you cannot play that game. Like neutrons cannot play this game. Nothing is attracted to or repelled by neutrons, and neutrons cannot attract or repel anything. So you've got to have electric charge. It happens to be measured in coulombs. So let me ask you another question. Suppose I tell you, here is Coulomb's law. Let me just write the number, 1 over 4 pi epsilon 0. How are you going to test that this law is correct? Okay, I'm giving you a bonus. You don't have to discover the law. I'm giving you the law. All you have to do is to verify it. And don't use any other definition other than this law itself. How will you know it depends on Q1 and Q2 in this fashion? How will you know it depends on R in that fashion? That's what I'm asking you. Can anybody think of some setup, some experiments you will do? Let me ask an easier question. How will you know it goes like 1 over R squared? Yep.
Vary the distance between them and show that the force falls off.
Well, you're right that if you vary the distance between them and show the force falls like that, but how do you know what the force is? Yes? What was your plan? You're right, both of you are right. You can maybe hold this guy fixed and let this go and see how it accelerates. And if you knew the mass of this guy, then you know the force. Then you can vary the distance to another distance, maybe half the distance. At half the distance, if you get 4 times the force, you verified 1 over R squared law. Other one is with a spring. You can take a spring, say maybe there are 2 metals, uncharged objects. Then you dump some charge on this and some charge on that, and then the spring will expand, and you can see what force the spring exerts, and see if it's proportional to 1 over R squared. That's how Newton deduced the 1 over R squared force law. He found the acceleration of the apple is 1 over 3,600 times the acceleration of the moon towards the Earth. And the moon was 60 times further than the apple, and 60 squared is 3,600. That's how we found 1 over R squared. Now, he's very lucky. It could have been 1 over R to the 2.110 or 1196, but it happens to be exactly 1 over R squared. Anyway, that's how we can find, even if it's not 1 over R squared, if it's 1 over R cubed or 1 over R to the 4th, whatever it is, you can find by taking 2 charges. See, we don't have to know what Q1 and Q2 are. That's what I'm trying to emphasize here. If all you're trying to see is, does it vary like 1 over R squared, keep everything same except R. Double the R and see what happens. And best way is what you said, watch the acceleration. And if it falls to 1/4 of the value for doubling the distance, it's 1 over R squared. All right, suppose I got 1 over R squared. I want to know it depends on the charges as the first power of Q1 and first power of Q2. So how should we do that? And don't say put 10 electrons once and then 20 electrons, because you cannot see electrons that well. And in the old days, people did not even know about electrons, and yet they managed to test this. So how will you vary the charge in a known way? Yep?
You could have many identical spheres and then keep touching them to each other.
Okay, many identical spheres.
And then put charge on one, and then touch it to the second one, and you'll get half as much.
Very good. Let me repeat what she said. First, you take many identical spheres. Well, I'm not going to even try to draw identical spheres because I haven't learned how to draw spheres. But let's imagine you got a whole bunch of these guys. You put some charge on this. You don't know what it is, okay? We don't know what Q is. We're trying to find out. You don't have to know what Q is. So let this be one of the objects. That's my Q. For the other object, keep a fixed object containing some other Q. This has got charge Q. Don't vary the R. Question is, can you change Q to Q over 2? And her answer was, if it's got some charge, maybe plus, bring it in contact with the second identical sphere. If it really is identical, you have to agree that when you separate them, they must exactly have half each. That's a symmetry argument, because for any reason you give me for why one of them should have more, I will tell you why the other one should have more. You cannot. So they will split it evenly, and therefore charge will split evenly to Q over 2 here and Q over 2 here. Then you can take this and put it there. You've got Q over 2. Then you can do other combinations. For example, you can take this Q over 2 and connect it to the ground, so it becomes neutral. So this has got 0 again. You can touch that with the Q over 2 and separate them. Then each will have Q over 4. So in this way, you can vary the charge in a known way. Maybe half of it, double it. I give you some homework problem where you want to get 5/16 of a Coulomb. By enough spheres, you can do that. Again, what I want you to notice is that you did not know what Q was. But all you knew is that Q went to Q over 2 when you brought two identical spheres and separated them. That's how we can find it depends linearly on Q1. Of course, it also depends linearly on Q2, because it's up to you to decide who you want to call Q1, who you want to call Q2. Okay. So I want you people to understand all the time that you should be able to tell me how you'll measure anything. Okay, that's very, very important. That's what you should think about. If you think in those terms, you'll also find you're doing all the problems very well. If you're thinking of pushing symbols and canceling factors of pi, you won't get the feeling for what's happening. So everything you write down, you should be able to measure. If you say, oh, I want to measure the force, you got to be sure how you'll measure it. And one way is, like you said, find m times a. If you knew the m, you can measure the force. But everything, make sure you can measure it. If I give you a sphere charged with something, then of course we got to decide. Suppose I give you a sphere, it's got some charge, and I want you to find out how much charge is on that sphere. This time I want you to tell me how many coulombs there are. What will you do? What process will you use? Well, then you have a problem, because you are not able to figure out whether, if I tell you here's an object, it is 3 meters long, you can test it, because you'll go and bring the meter stick from the Bureau of Standards and measure it 3 times. I'm asking you, if I give you a certain charge and say how much charge is there, by what process can we calibrate charges? Yep.
Put it in the vicinity of a reference charge and measure the acceleration.
That's correct. If you knew one standard charge, somehow or other, you knew its value, then bring the unknown one next to it, put it at a known distance, right? You know the r, you know the 4 pi, you know the epsilon. You find the force, you can find this charge. So all we need to know is how to get a reference charge, right? So how do I know something has a Coulomb? How do I get 1 Coulomb of charge, just to be sure? You know what you could do? Because you haven't defined yet the reference, right? So you should think about how will I get a Coulomb charge, or any other charge. So I could take these 2 spheres that she talked about, each with the same charge Q. We don't know what it is. I put them at 1 meter distance, and I measure the force, namely how hard should I hold one from running away to the other one. Once I got the force, the only thing unknown in the equation is Q times Q. I know R, I know 1 over 4 pi epsilon, I can get Q. So every time you write something, think about how you will measure it, because in that process, you're learning how the physics is done. If you try to avoid that, you'll be just juggling equations, and that doesn't work for you, and that doesn't work for me. Anybody who wants to do good physics should be constantly paying attention to the physical phenomenon and not to the symbols that stand for physical objects. All right. So the final thing I want to do in this connection is to give this number I mentioned, F gravity over F electric. I said gravity is 10 to the minus 40 times weaker. Well, you have to be precise on how you got the number. See, it's not like selling toothpaste, where you can say it is 7.2 times whiter. I don't know how those guys measure whiteness in a unit with 2 decimal places. But you know, that's a different game. It's not subject to any rules. But here, you have to say how you got the number. In what context did you make the comparison? It'll turn out the answer does depend on what you chose. There'll be some variations, but those tiny variations are swamped by this enormous ratio I will get. So what you could do is take any 2 bodies and find the ratio of gravity to electric force. One option is to take 2 elementary particles, whichever 2 you like. So I will take an electron and a proton, but you can take electron and a positron, or proton and a proton, doesn't matter. These 2 guys attract each other gravitationally and electrically. So I will write the force of gravitation, which is G, mass of the proton, mass of the electron, over r squared, divided by q electron, q proton, over 4 pi epsilon 0, times 1 over r squared. Notice in this experiment, in this calculation, r squared does not matter. So you don't have to decide how far you want to keep them because they both go like 1 over r squared. So you can pick any r. So whatever you pick is going to cancel. And you will be left with this number. Q1, Q2, and the 1 over 4 pi epsilon is 9 times 10 to the 9. So now we put in some numbers. So G is 10 to the minus 11 with some prefactors, maybe 6 in the case. I'm not going to worry about prefactors. But the mass of the proton is 10 to the minus 27 kilograms. Mass of the electron, 10 to the minus 30 kilograms. So don't say, how come they all have these nice round numbers? They are not. There are factors like 1 and 2. I'm not putting them because I'm just counting powers of 10. Q1 is 1.6 times 10 to the minus 19. So 2 of those Q's is 10 to the minus 38. Then 9 times 10 to the 9 is roughly 10 to the 10. If you do all that, you will find this is 10 to the minus 40. So it is some typical situation that you took, and you found this ratio of forces. So if there are 2 elementary particles, which are like the building blocks of matter, and you brought them to any distance you like, you compare the electric attraction to the gravitational attraction. So one question is, if gravity is so weak, how did anyone discover the force of gravity? If all you had was electrons and protons, you will have to measure the force between them. Suppose you knew only about electricity, didn't know about gravitation. One way to find there is an extra force is to measure the force to an accuracy good to 40 decimal places. In the 40th decimal place, you find something is wrong. You fiddle around and figure out the correction comes from m1, m2 over r squared. But that's not how it was done, right? You guys know that. So how did anyone discover force of gravity when it's overwhelmed? Yes?
Most things are neutral.
Yes. Most things are electrically neutral. In other words, electric force, even though it's very strong, comes with opposite charges. It can occur with a plus sign or with a minus sign. Therefore, if you take the planet Earth, it's got lots and lots of charges in every atom, but every atom is neutral. You got the moon, ditto, lots and lots of atoms, but they're all neutral. But the mass of the electron does not cancel the mass of the proton. So mass can never be hidden, whereas charge can be hidden. Mass never cancels. That's the reason why, in spite of the incredible amount of electrical forces they are potentially capable of exerting, they present to each other neutral entities. Therefore, this remaining force, which is not shielded, is what you see and has a dramatic role in the structure of the universe, force of gravity. But most cosmological calculations, you can forget mainly the electric force, it's all gravitational force. That's because electricity can be neutralized. So you cannot hide gravity. Everything has mass. Even photons, which have no mass, have energy. They're also attracted by gravitation. So gravity cannot be hidden. And that's the origin of something called dark matter. So how many guys heard about dark matter? Okay. Anyone want to volunteer? Someone whose name begins with T. Anybody name begins with T and also knows the answer to this? Okay, I don't. The trouble is, you people are plagued with one quality which is not good for being in physics, namely you're modest. So you don't want to tell me the answer. So I have to give an excuse for whoever gives the answer. If your seat has a number, 142. Anybody is in seat 142? Maybe they're not even numbered. Look, okay, anybody with a red piece of clothing knows the answer to this? Go ahead, yes.
Any matter that doesn't produce light.
Pardon me?
Any matter that's not visible. So like if you're looking
Right.
like through a telescope, anything that is not going to produce any sort of visual electromagnetic.
Right. Basically, there's no way you can see it. And there's dark matter right in this room. Okay? And there's dark matter everywhere. But the way people found out there is dark matter, do you know how that was determined? Yep.
The rotation of galaxies didn't line up with the matter that was visible.
So yes, maybe one example I can talk is about our own galaxy. So here's our visible galaxy, okay? The old spiral. Now, if something is orbiting this galaxy, just by using Newtonian gravity, by knowing the velocity of the object as it goes around, you can calculate how much mass is enclosed by the orbit. That's a property of gravitation. From the orbit, you can find out how much mass is enclosed. So what you will find is, if you found something orbiting the center of the galaxy at that radius, you'll enclose some mass. If you take objects with bigger and bigger radius, you will enclose more and more mass. Till you find orbits as big as the galaxy, then the mass enclosed as a function of radius should come and stop. Because after that, the orbit's getting bigger, but not enclosing any more mass. But what people found is that even after you cross the nominal size of the galaxy, you still keep picking up mass. And that is the dark matter halo of our galaxy. So it's dark to everything, but you cannot escape gravity. That's what I meant to say. You cannot avoid gravitational force. So people are trying to find dark matter. People at Yale are trying to find dark matter. The thing is, you don't know exactly what it is. It's not any of the usual suspects, because then they would have interacted very strongly. So you're trying to find something not knowing exactly what it is. You got to build detectors that will detect something, and you go through it every day in your lab, and you're hoping that one of these dark matter particles will collide with the stuff in your detector and trigger a reaction. Of course, there'll be lots of reactions every day, but most of them are due to other things. That's called background. You got to throw the background out, and whatever is left has got to be due to dark matter. And again, how do you know it's dark matter? How do you know it's not something else? Well, you can see that if you're drifting through dark matter in a moving Earth, you'll be running into more of them in the direction of motion and less in the other direction, because you're running into the wind. So by looking at the direction dependence, you can try to see if it's dark matter. Anyway, dark matter was discovered by simple Newtonian gravitation. The particles that form dark matter are very interesting to particle physicists. There are many candidates in particle theory, but the origin of the discrepancy came from just doing Newtonian gravity. All right. Now, the final thing today, before we break, is that there is one variation of Coulomb's law. By the way, I do not know your mathematical training and how much math you know. So you have to be on the lookout. So if I write something that looks very alien to you, you got to go take care of that. In particular, how to do integrals in maybe more than one dimension. Anyway, what I wanted to discuss today is the following. We know how to do Coulomb's law due to any number of point charges. So if you put another charge Q here, you want the force on this guy due to all these. You draw those lines, you take the 1 over r squared due to that, 1 over r squared due to that, add all the vectors. That's very simple. But we will also take problems where the charge is continuous. So here's an example. Here's a ring of charge. The ring has some radius. You pick your radius, r, and the charge on it is continuous. It's not discrete. Or it could be in real life, everything is discrete, but to a coarse observer, it will look like it's continuous. So we can draw some picture here. Charges all over the ring, and lambda is the number of coulombs per meter. That means if you snipped 1 meter of the wire, it'll have lambda coulombs in it. And you want to find the electric force on some other charge Q due to this wire. So you cannot do a sum, and you have to do an integral. That's what I'm driving at. And I'm going to do one integral, then we'll do more complicated ones later. So I want to find the force on a charge q here. So what I will do is I will divide this into segments, each of length, say, dl. Then I will find the force of the charge here, dF. I will add the forces due to all the segments. Now, force of this segment will be the charge. This segment is so small, you can treat it as a point charge, and the amount of charge there here is lambda times dl. That's the q1. The q2 is the q I put there. Then there's a 4 pi epsilon 0 r square. R square will be this distance z times this radius r will be, maybe I shouldn't call it r, let me call it capital R. Then it's r square plus z square. That's the distance. But now that force is a vector, it's pointing in that direction. But I know that the total force is going to point in this direction, because for every guy I find in this side, I can find one in the opposite direction pointing that way. So they will always cancel horizontally. The only remaining force will be in the z direction. So I'm going to keep only the component of the force in the z direction. I denote it by dF in the z direction. For that, you have to take this force and multiply by cosine of that theta. I hope you know how to find the component of a force in a direction. It's the cosine of the angle between them. That angle is equal to this angle, and cosine of this is z divided by r squared plus z squared under root. That is the dF due to this segment, and the total force in the z direction is the integral of this. And what's that integrate? Lambda, q, all these are constant. R, z, everything is a constant. You have to add all the dLs. If you add all the dLs, you will get the circumference. In other words, this is going to be lambda q z divided by 4 pi epsilon 0 r squared plus z squared with 3 over 2 integral of dl. Integral of dl is just 2 pi r. In other words, every one of them is making an equal contribution, so the integrand doesn't depend on where you are in the circle, so you're just measuring the length of the circle. So that's the answer. The force looks like lambda times 2 pi r. What is that? Lambda is the charge per unit length. That times the length of the loop is the charge on the loop. This is the charge you're putting there. It's divided by 4 pi epsilon 0 divided by r squared plus z squared, the 3 over 2. That's an example of calculating the force, which will be in this direction. Now, once you've done this calculation, you may think maybe I missed a factor of pi or a factor of e, something. Can you think of a way to test this? What test would you like to apply to this result? Yep.
We're going to put the z equal to 0 and have it in the middle. There should be no forces on it.
Very good. What he said is, if you pick z equal to 0, you're sitting in the middle of the circle, and you're getting pushed equally from all sides, and you better not have a force, and that's certainly correct. This vanishes when z goes to 0. Anything else? Any other test? Yep.
You could put it underneath by negative z, and the force should be negative.
Yes, it will point down and be negative, that's correct. But how about the magnitude of the force itself rather than just the direction? Yep.
As you go infinitely far away, it should look like a point card.
Yes. If you go very, very far, someone's holding a loop, you cannot see that it's even a loop. It's some tiny speck, and it should produce the field. So what field should it produce? It should produce the Coulomb force, Q1, Q2, over 4 pi epsilon 0 times distance squared. And when z is much, much, much bigger than r, this is 1 kilometer, this is 2 inches, you forget this, you get z squared to the 3 over 2 is then z cubed. That means the whole thing here reduces to 1 over z squared, and it looks like the force between 2 point charges. So I would ask you, whenever you do a calculation, to test your result. Okay, before going, I got to tell you something about those who come late. I realize that you guys come from near and far. So when you come late, let me give you my preference for doors. Okay, door number 1 is that one. That's the least problematic. Door number 2 is this one, because in the beginning of the lecture, I'm usually on that side of the board, so you guys can come in. Door number 3 is that one, where Jude is taking the picture, but do not stand in front of the camera and contemplate your future. If you do, I will make sure you don't have a future, okay? So don't do that. If you come fashionably late, never come through that door, maybe this one. In fact, if you come through that door, because I've reached this side of the board, you're very, very late. So I think you should take the day off and start fresh next time. All right. Okay, thank you. Because if you don't know what force is acting on a body, you cannot predict anything. So you can go back to the spring and say, I want to know what force the spring exerts when it's pulled by various amounts. Well, you pull it by some amount x, you attach it to a known mass, and you find the acceleration, and that's the force. And if you plot it, you will find f as a function of x will be roughly a straight line, and it will take the form f equals minus kx. That k is called the force constant. So this is an example of you're finding out the left-hand side of Newton's law. You've got to understand the distinction between f equals minus kx and f equals ma. What's the difference? This says if you know the force, I can tell you the acceleration. But it's your job to go find out every time what forces might be acting on a body. If it's connected to a spring, and you pull the spring and it exerts a force, someone's got to make this measurement to find out what the force will be. All right, so that's one kind of force. Another force that you can find is if you're near the surface of the earth, if you drop something, it seems to accelerate towards the ground. And everything accelerates by the same amount, g. Well, according to Newton's laws, if anything is going to accelerate, it's because there's a force on it. Therefore, the force on macroscopic, you can describe the way you do with Newtonian mechanics or electrodynamics. You don't need quantum theory. All right, so now we'll start with the brand new force of electromagnetism. But before doing the force, I got to remind you people of certain things I expect you all to understand about the dynamics between force and mass and acceleration that you must have learned last term. But I don't want to take any chances. I'm going to start by reminding you how we use this famous equation of Newton. So we have seen this equation probably in high school, but it's a lot more subtle than you think. Certainly a lot more subtle than I thought when I first learned it. So I will tell you what I've figured out over these years on different ways to look at f equals ma. In other words, if you had the equation, what's it good for? The only thing anybody knows right away is A stands for acceleration, and we all know how to measure it. By the way, anytime I write any symbol on the board, you should be able to tell me how you'll measure it. Otherwise, you don't know what you're talking about as a physicist. Now, acceleration, I think I won't spend too much time on how you measure it. You should know what instruments you will need. So I will remind you that if you have a meter stick or many meter sticks and clocks, you can follow the body as it moves. You can find its position now, its position later, take the difference, divide by the time you get. So I got to start by telling you the syllabus for this term. Not the detailed one, just big game plan. The game plan is we will do electromagnetic theory. Electromagnetism is a new force that I will introduce to you and go through all the details. And I will do optics. And optics is part of electromagnetism. And then near the end, we will do quantum mechanics. Now, quantum mechanics is not like a new force. It's a whole different ballgame. It's not about what forces are acting on this or that object that make it move or change its path. The question there is, should we be even thinking about trajectories? Should we be even thinking about particles going on any trajectory? Forget about what the right trajectory is. And you will find out that most of the cherished ideas get destroyed. But the good news is that you need quantum mechanics only to study very tiny things, like atoms or molecules. Of course, the big question is, where do you draw the line? How small is small? Some people even ask me, do you need quantum mechanics to describe the human brain? And the answer is yes, if it is small enough. So I've gone to parties where after a few minutes of talking to a person, I'm thinking, okay, this person's brain needs a fully quantum mechanical treatment. But most of the time, everything velocity. Then find the velocity now, find the velocity later, take the difference, divide by time, you get acceleration. So acceleration really requires 3 measurements, 2 for each velocity. But we talk of acceleration right now because you can make those 3 measurements arbitrarily near each other, and in the limit in which the time difference between them goes to 0, you can talk about the velocity right now and acceleration right now. When you're in your car, the needle points at 60, that's your velocity right now. It's an instantaneous quantity. And if you step on the gas, you feel this push, that's your acceleration right now. That's a property of that instant. So we know acceleration, but the question is, can I use the equation to find the mass of anything? Now, very often when I pose the question, the answer given is, go to a scale, weighing machine, and find the mass. And as you know, that's not the correct answer because the weight of an object is related to being near the Earth due to gravity, but the mass of an object is defined anywhere. So here's one way you can do it. Now you might say, well, take a known force and find the acceleration it produces. But we haven't talked about how to measure the force either. All you have is this equation. The correct thing to do is to buy yourself a spring, then go to the Bureau of Standards and tell them to loan you a block of some material, forgot what it is. That's called a kilogram. That is a kilogram by definition. There is no God-given way to define mass. You pick a random entity and say that's a kilogram. So that's not right and that's not wrong. That's what a kilogram is. So you bring the kilogram, you hook it up to the spring, and you pull it by some amount, maybe to that position, and you release it. You notice the acceleration of the 1 kilogram, and the mass of that thing is just 1. Then you detach that mass. Then you ask, then the person says, what's the mass of something else? I don't know what the something else is. Let's say potato. Then you take the potato or anything, elephant, here's potato. You pull that guy by the same distance. And you release that, and you find its acceleration. Since you pulled it by the same amount, the force is the same, whatever it is. We don't know what it is, but it's the same. Therefore, we know the acceleration of 1 kilogram times 1 kilogram is equal to the unknown mass times the acceleration of the unknown mass. That's how, by measuring this, you can find what that mass is. So in principle, you can find the mass of everything. So imagine masses of all objects have been determined by this process. Then you can also use F equal to ma to find out what forces are acting on bodies in different situations.